Here we're going to look at the solutions to the harmonic oscillator problem in quantum mechanics. The details of the solution are in another video lecture. Here we're just going to summarize the results of the solving the Schrodinger equation. Solving the Schrodinger equation involves getting wave functions and energies. So here they are. These are the wave functions and these are the energies for a harmonic oscillator. Let's look at the solution here in more detail for the wave function. We've defined a parameter alpha as m times frequency over h bar. Okay, so let's look at that parameter alpha is m times frequency over h bar. Let's look at the units of that. Mass, let's put SI units there, kilogram, frequency, inverse seconds. H bar has units of joule times second. A joule is a kilogram meter squared per second squared. That's the joule, and you multiply that by seconds. So what you find is that alpha has units of 1 over meter squared. That's not mass, that's meter squared. So it has units of 1 over length squared, or alpha has alpha to the 1/2. Has units of 1 over length. Okay, so if we go back here, we have here over here alpha to the 1/2 x. So alpha has units of inverse length, and x is our spatial coordinate. So this in here in the parentheses is unitless. Also, in this exponent, we have alpha, which has units of 1 over length squared, and x is length squared, so this also is unitless. So our parameter alpha has units of 1 over length squared. Okay, so now let's look at this in more detail. Here, these constants here, well, actually, let's reproduce that here. So these constants here are the normalization constants. Normalization constants, they don't depend on x. This is the solution to the Schrodinger equation for harmonic oscillator. This then is n, where n is a quantum number. And when you solve the Schrodinger equation in detail, you find that n is equal to 0, 1, 2, and so on. So now quantum number starts at 0, not starting at 1 like it did for particle in a box. So we have these wave functions, each state defined, each eigenstate defined by a quantum number n. Normalization, these are interesting. These are Hermite polynomials. Hermite polynomials. And this function here, that e to the minus alpha x squared over 2, is a Gaussian function. Gaussian. All right, named after two famous mathematicians of the 1800s, Hermite and Gauss. All right, let's first take this apart. Well, the normalization is not real exciting. It's just a number, depending upon what alpha is. Remember, alpha was defined as the square root of k over, alpha was defined, I just go back and see what alpha was defined, yeah, m omega over h bar. Where m is the mass of particle that's doing the oscillation. Omega is the frequency of oscillation in units of radian per second, and h bar, as we know, is Planck's constant divided by 2 pi. Okay, so those are just constants there. Let's look at this Gaussian function, e to the minus alpha x squared over 2. All right, let's see what this means. As we said, that's a Gaussian function. Let's write the Gaussian function in a way that most mathematicians do. That's e to the minus x squared over 2 sigma, let me just, the pen's not working very well today, 2 sigma squared, where you may recognize this, or maybe not. Sigma is called the standard deviation. So if we plot this Gaussian curve, and we'll put this at 0, we have the common bell-shaped curve that gives you a distribution, for instance, of SAT scores or various other things, and the width of this distribution is the standard deviation sigma. If we compare that to that term in the solution of the Schrodinger equation, which we've written as minus alpha x squared over 2, we find that the standard deviation, sigma, is defined as 1 over the square root of alpha. And again, alpha has units of meter squared, or inverse meter squared, so this has units of meter, or length. All right, so the width of this Gaussian distribution is governed by alpha, which in turn is governed by the mass of the particle and the frequency by which it oscillates. Okay, so that's the Gaussian part of the solution to the Schrodinger equation for a harmonic oscillator for these wave functions. So what this will do will be multiply everything here by this envelope. So you're taking whatever that Hermite polynomial is, whatever this is, and the normalization constant, and then multiplying it by this envelope. That's what that Gaussian part does. Now let's look at these Hermite polynomials, h of n and these Hermite polynomials are a function of alpha to the 1/2 x. So again, this is unitless because alpha to the 1/2 has units of 1 over length, and times length, that'll be unitless. And this also is characterized by a quantum number n. So depending upon what n is, you get a different Hermite polynomial. Note that the Gaussian function doesn't depend on n, the quantum state, or the normalization. So all the quantum behavior is encompassed in this Hermite polynomial h of n. All right, so let's see what h of n looks like. Oh, well, you don't need to, you look in the textbook, or we can go to Wikipedia. Here's the Wikipedia article on Hermite polynomials. And let's just see what they look like. Well, if you read this, there are two different kinds of Hermite polynomials. There's the ones that people who work in math, probability, use. Let me make this a little bit bigger here. And those are called the probabilist Hermite polynomials. And then there's a physicist Hermite polynomials. We're going to use the physicist Hermite polynomials. Let's see what they look like. All right, so here they are. That's a plot. We'll get to the plot in just a minute. N equals 0. Oh, that's a pretty simple function. It's just equal to 1. When n is equal to 1, this is equal to 2x. When n equal to 2, the Hermite polynomial is 4x squared minus 2. Now, don't be confused. This is not distance x. In fact, this is a unitless number, because what we're doing, remember, h of n, h sub n is a unitless number. So this x, which is actually distance, is different from the Wikipedia x, which is a unitless number. So we have to substitute in square root of alpha times x for this value of x. So we just remember that. Oh, so I got 0, 1, 2, 3, there it is, and so on. So these are polynomials, and h3 n equal 3 means this is the highest order, is a third order polynomial. h9, the highest order polynomial is, or power of x is 9. That's interesting. Also note that 2, you have a power of x equal 2. 4, you have 4 and 2. 6, you have 6 and 4 and 2. So things that have even values of n have only even powers of x. Odd values of n, like 1, 3, and 5, and so on, have odd powers of x here. Okay, so even and odd. So this introduces the concept of even functions and odd functions. So there are two different kinds of Hermite polynomials, and if you look at the details to the solution, you'll see where these come from. We have the even, that corresponds to n equals 0, 2, 4, and so on. And then you have the odd polynomials, where n is equal to 1, 3, 5, and so on. All right, for an even function of x, definition, if you take f of minus x, you get the same function back again, f of x. On the other hand, if a function f of x is odd, then if you take f of minus x, what you get is the negative of the function f of x. So by replacing x with minus x and see if you get either the same function or a different function, then you can determine whether you have an even or odd function. So let's look at, let's say look at h1. So h1 of x, and again, this x is a different x from the x we're using. This is a dimensionless number. h1 of x, we say, is 2x. Now, is h1 even or odd, or it could be neither even nor odd? So let's just do that. Let's put f, or h of x. Let's put h of x, sorry. h of x is equal to 2x. h of minus x is equal to, we replace x with minus x, minus 2x. So this is an odd function. Okay. Let's look at h2 of x. So h2, where now we quantum numbers even of x, that was equal to, short memory here, 4x squared minus 2. So h2 is h1 here. h2, we'll just do right here, h2 of minus x is 4 times minus x. You replace x with minus x squared minus 2. And that's equal to 4x squared minus 2. So h of x equals minus h of x. Oh, that's kind of interesting. So h2 of x is an even function. So you can go all through here and find that, h1, h3, h5, where n is odd, are odd functions. h0, 2, 4, and so on, where n is even, are even functions. And that'll be important when we start calculating expectation values and so on. So even and odd functions. And also they're polynomials and so on. So let's graph these. Here's the Wikipedia graph, h1 of x, or h0 of x, because n, the lowest n could be is 0. Okay, let's see what that looks like. That's that red line here. That's h1 of x. It's just a constant equal to 1. Okay, h1 of x is just a straight line 2x. So there it is. That straight line there is a plot of the Hermite polynomial. h2 of x, 4x squared. So that would be this one here, goes down this way and goes up. It's just a quadratic, x squared. And the third one is, let's see if I can find that. It goes, it must be this one. Third one is n equal 2, goes up and down and up like that. N equal 4 is this one. N equal 5 goes up and down like this, and so on. Okay, so now we understand sort of Hermite polynomials. They're odd and even polynomials. Let's go back and put those in. So we go back to the original equation. So we have some understanding of Hermite polynomials, and we have some understanding of these Gaussian functions, and this is just a number. So let's go ahead and plot the wave functions. Let's put all this together and plot the wave functions. And I've done that in an Excel spreadsheet, which I'll put on Blackboard. So here is the wave function for the n equals 0. All right, so does that make sense? We want the Hermite polynomial for n equals 0. The Hermite polynomial for n equals 0 is just 1. Oh, okay. So what we're plotting here is just that's equal to 1. We're just plotting with a normalization factor the Gaussian function. So that's why n equal 1 looks like this Gaussian function here. And remember that we said the standard deviation is 1 over alpha, which is related to the spring constant. So let's change the spring constant here to say 500. It looks like the width narrows. If we decrease the spring constant, say, to 1, it increases. So the spring constant governs how wide the distribution is, and also well, just let's go back and see what that looks like. It's mass times omega, and alpha. Omega was equal to the square root of k over m, so this is equal to the square root of k over m. So you would expect that alpha, the standard related to the standard deviation, would depend on the spring constant and also on the mass, and that's what we found. All right, and what I've done was attached a proton to a fixed surface, and now the proton is oscillating, and this is the mass of the proton. Put everything in SI units, so this is actually distance in meter. All right, so there's the harmonic oscillator wave function, which is a combination of the normalization constants, the Hermite polynomial, and the Gaussian function. All right, let's go to n equal 2, or n equal 1. Sorry, it starts at 0. Here's the n equal 1. Oh, look, it goes through. So n equal 1 has one node. The wave function goes through 0. Let's look at n equal 2. There's the n equal 2 wave function. It's interesting. If we look at the n equal 1, let's go back to the Wikipedia article and look at the graph for the n equal 1. The n equal 1 is this green line here. Note that if you extrapolate this all the way out to infinity, you'll get the Hermite polynomial being equal to infinity, and that's not a good behavior for a wave function. You want it to die off toward infinity. Well, luckily, it's just not the Hermite polynomial that contributes to the wave function. It's also the exponential function. So this exponential function, even though Hermite polynomial is going to infinity as x goes to infinity, this here is decreasing fast enough, so it's going to beat down that Hermite polynomial and force it down to 0. So that's what we found, force it down to 0. So even though n equal 1, you'll have a straight line for the Hermite polynomial. That exponential function you're multiplying by will make it go to 0. Like that. N equal 2, well look, 1, 2 nodes, and it's going to 0 because of that exponential term. N equal 3 and so on. Let's go to n equal 10. Here it is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes for the n equal 10. So that's what the wave functions look like when you combine the normalization constant, the Hermite polynomial, and that Gaussian damping function. Let's go over here and let's look at probability density, where we plot, no, this should be psi squared. All right, so if you take the Gaussian function and multiply it there, yeah. This was the n equal 1 state. When you multiply that, what do you think? By itself, the square, that'll go up, be all positive. Can't have negative probability. So here we are for the n equal 1 state. Here's the n equal 2 state, the n equal 3, and here's the n equal 10 state. So these are probability density as a function of distance, as this proton, in this case, proton is oscillating. Okay, so we know something about the wave function, and we know about those two functions that constitute the wave function. So let's plot the probability density as a function of distance. This spring is stretching. Let's call this 0. So that will be our reference point here. And let's do it for the n equals 0 state. For the n equals 0 state, we said that it's just essentially the square of the Gaussian function, goes up and then down like this. This is the probability density. Let's put on top of this the potential for the classical harmonic oscillator. So here's the potential for the classic harmonic oscillator. So this is the quantum mechanical for n equals 0. This is the potential for classical. Now for classical, you have a certain amount of energy, and you can't exceed that energy. So it has to stop here when it stretches, and it goes back down, compresses, stops here, and so on. So these are the limits by which x by which you can have x. You can't go further than that because you just don't have enough energy classically. But quantum mechanically, that's called, by the way, the turning point of the classical oscillator. It turns out that you have some probability density that the quantum mechanical oscillator is further than you would expect classically. So the quantum mechanical can stretch further and you could stretch that spring even more than you could classically. That's interesting. Also, let's look at the probability density again for, say, the n equals 0 state. It goes something like this. And let's look at the probability density, or the probability density for classical. So this will then be the quantum mechanical. Classically, what do you find? Well, you find as the particle is starting up here, goes faster and faster and faster, and then goes slower and slower and slower. So where it's going fast here, it'd be less likely to find the particle than when it's actually stopped up here and turns around, or stopped up here and turned around. So for a classical oscillator, the probability distribution would be something like this, where you're least likely to find it here and most likely to find it up there. So for the n equals 0 state, you just have the opposite prediction in terms of where it's most probable. Quantum mechanically, it's most probable to find it right there, where you have the maximum kinetic energy and the lowest potential energy. And but classically, you expect it to find here out at the end, where you have the most potential energy and the smallest kinetic energy. All right, so that's some things that you would not predict classically that show up quantum mechanically. So that's some discussion, some things, interesting properties about this wave function. It has the Hermite polynomials, can be odd or even. It's multiplied by a Gaussian, which forces the function to go to 0. And the predictions from these wave functions are not what you expect classically. Now let's concentrate on energy, the quantum mechanical energies. Again, energy is quantized. You can only measure this these kinds of energies. All right. So energy, I'll just reproduce this. Energy for a harmonic oscillator is n plus 1/2 h bar omega. And note that h bar is h divided by 2 pi, and that 2 pi times the frequency nu is equal to omega, and therefore you can rewrite this as n plus 1/2 h nu. So h bar omega is the same as h nu, where nu is frequency in hertz or cycle per second. Omega is frequency in radian per second. Well, we use h bar omega. Okay, so there it is. So n, again, n is a quantum number, and n is an integer, which can go from 0 all the way up to infinity. Well, that's interesting, because when n is equal to 0, the energy for the n equals 0 state is 1/2 h bar omega. This is called the 0 point energy of a quantum mechanical oscillator. This means that if you take away, if you go to the lowest energy state, take away all heat and whatever energy else you have, the oscillator is still vibrating. Ooh, that's interesting. So it's oscillation, 0 point energy. So if you look at, say, the energy ladder here, n equals 0, n equal 1, n equals 0 will be 1/2 h bar omega. N equal 1, that'll be 3/2 h bar omega. N equal 2, you have 5/2 h bar omega. So you'll have evenly spaced energy levels whose separation is h bar omega. And again, omega is equal to the square root of the spring constant of the oscillator divided by mass. All right, if we look again, let's say, compare quantum mechanics with classical mechanics, here's the potential here. There's the potential. This is distance. We're setting 0 right there at the bottom of that classical potential. Now you've taken away all energy, which means you're taking away all kinetic energy. Classically, you expect that the energy, so I'm going to just put energy this way, and this is equal to 0. Classically, you expect if you take away all the kinetic energy, and you have no potential energy, so it's 0. But what you find quantum mechanically is you take away all that kinetic energy, say to cool you into 0 Kelvin, you'll still have a non-zero energy. This energy, the 0-point energy, is 1/2 h bar omega. All right, so that's an important point about these energies. All right, so that pretty much wraps up our discussion of solutions to the Schrodinger equation. The last topic we'll consider when we're considering here the solution to the Schrodinger equation for a harmonic oscillator, we'll consider the correspondence principle. So if we remember what we had before, let's see, here we predict classically that the probability of a classical oscillator, you're least likely to find it right there when it has the maximum kinetic energy and minimum potential energy. But quantum mechanics says for the n equals 0 case that here you have the maximum probability at the center. So classically minimum probability, quantum mechanically you have maximum probability. So how do you reconcile this? Well, the way you reconcile this is using the correspondence principle, which says that the predictions you make from quantum mechanics have to agree with those you make from classical mechanics when the value of the quantum number becomes very large. All right, so let's see if we can explain that. Let's go back to our plot here. Here was the probability density, and you multiply it by some small volume here, you get the probability density for n equal 1. And we said, oh, it's maximum here at 0, but classically you expect that to be 0, expect that to be minimum classically. All right, let's go to n equal 2. Well, there it is, a minimum, but there's not that smooth curve you would expect. Let's do n equal 3. Oh, look, it's starting to look like that, the classical. Let's do n equal 4. Oh, yeah, it's high there, going down. And n equal 10. Well, here's the n equal 10. It's even looking more smooth now. The classical, remember, starts here, goes to minimum here. So if we just keep extrapolating this from n equal 10, extrapolate all the way up to n equal infinity, yes, indeed, we will find that the probability distribution we get from quantum mechanics will be equal to that which we predict from classical mechanics. And the separation, the number of nodes as n goes to infinity is equal to infinity. So you have essentially an infinite number of these up and down things, so it'll appear smooth to us when we use some measurement device that we cannot distinguish an infinitesimal separation in energy levels. So it looks like correspondence principle checks out. We predict using the quantum mechanics of a harmonic oscillator what we would measure classically for very large values of the quantum number.